Hi there, everybody. This is the lecture video for Chapter 5, Section 3. This is another short one, as promised. Today we'll be doing the opposite of what we did in the last section. We're taking the given probability and we're going to backtrack to find the value of the random variable. I think you'll do just fine. Just pay attention to the steps and keep the terminology and formulas straight. Okay, here we go. Welcome to the lecture video for Chapter 5, Section 3, Normal Distributions, Finding Values. Our objectives will be to find z-scores given the area under a curve, transform a z-score back into an x value, and then learn how to find a specific data value for a normal distribution given a probability. In a previous section, we were given a normally distributed random variable x, and we were asked to find a probability. Well, in this section, we're going to be given a probability, and we're going to reverse it. We're going to find the value of the random variable x. Let's say that we want to find the z-score that corresponds to a cumulative area of 0.3632. Well, the area is what is underneath the curve, so I know area. I need to figure out the z-score that marks that spot. So what you do is you look up 0.3632, not in the column and row headings, but in the body of the table. Because we're going backward in our process, it makes sense that we would look at the table backward too. We look at what we saw as our answer before, and then to the side for our row header and look up for the column header. In this case, we found 0.3632 in the standard normal table, then looked across and found the beginning part of our number, negative 0.3, then looked up for our column header, or the rest of the number, the hundredths place, 0.05. So our entire number is negative 0.35. Okay, let's do another one. Let's find the z-score that has 10.75% of the distribution's area to its right. First of all, let's get this into decimal form. 10.75 would be 0.1075. So the blue area is representing 0.1075. Now remember, I can't just look up 0.1075 in the table because we're looking at an area to the right, which is not represented in the tables. The area in the tables represent area to the left of z-scores. But we do know that the cumulative area under the curve is 1, so we can subtract 1 minus 0.1075 to get the area we're looking for, the remainder, which would be 0.8925. That is the area we look for in the table. So we do that next. We find 0.8925 in the standard normal table in the middle area. Then we look across to the side to find the beginning of the z-score. That would be 1.2 for this one. Then we look up for the hundredths place. For this, it's 0.04. So our entire number, or z-score, is 1.24. Now occasionally you're going to be asked for the z-score that corresponds to a given percentile, like this one, the 5th percentile. That's how you read this notation, 5th percentile. It's also 5%. We treat percentiles just like other decimal numbers. For this example, the 5th percentile is the same z-score that corresponds to an area of 0.05. The areas closest to 0.05 in the table are 0.0495 with a z-score of negative 1.65 and 0.0505 with a z-score of negative 1.64. Because 0.05 is halfway between the two areas in the table, use the z-score that is halfway between negative 1.64 and negative 1.65, which would be negative 1.645. How about the 50th percentile, or 50%? You actually know this one from other work we've done. Take a moment to think about this without looking it up in the table first. Okay, so hopefully what you were thinking is that 50th percentile means that it's at the center, so the z-score is 0. When the z-score is exactly at 0, the area is 1/2, or 0.5. So turn that around, and when the area is 0.5, the z-score is 0. Now look at your table to verify that the closest area is 0.5000, and it aligns with 00.00 or negative 00.00. It's on both tables. Okay, let's move on. What about the 90th percentile? Well, first of all, we convert it to a decimal and get 0.9. We look on the table and the closest area is 0.8997. So we look at the table and see that it corresponds to a z-score of about 1.28. So let's look at a way to use your calculator to find these. I do want to caution you that your answers on your calculator might be slightly different than what shows on the table. We're going to use the same menu we've used for a few sections now. Press the second key, then VARS to select the distribution menu. Arrow down and select the 3 inverse normal function. Press Enter. Type the area in decimal form. Depending on your calculator, you may need to type in or just verify the mean is set at 0 and the standard deviation is 1. You may not have to do that at all. Depends on your calculator. Don't worry about it if you don't. Then press Enter as many times as you need to calculate. Let's do this for the question we just did for 90th percentile. Press the second key, the VARS button, arrow down to 3 inverse norm function, press Enter, type 0.9. Mine already has a 0 for mean and 1 for standard deviation. If yours does not have those in there, make sure you put that. 0 for mu or mean and 1 for sigma or standard deviation. And if it already has it, you press Enter to go through those. If it doesn't have it, you don't have to enter those. Then press Enter, Enter, or however many times you need to for it to calculate. Did you get something close to 1.28? That's what was on the table, so good job. Okay, so let's say I want to go one step further. I've found the z-score from the area, but now I want to find that original x value from the z-score. Guess what? We can do that. There's a fairly simple formula we can use to find that. To transform a standard z-score to a data value x in a given population, use the formula x equals mu plus z times sigma, or translated, x value equals the mean plus the z-score times the standard deviation. This actually was derived from the standard formula for x. Z equals x minus mu divided by sigma, or z-score equals x value minus mean divided by standard deviation. When you algebraically solve for x, you end up with this formula, so you're using the same formula. Let's try it out, shall we? A veterinarian records the weights of cats treated at a clinic. The weights are normally distributed with a mean of 9 pounds and a standard deviation of 2 pounds. Find the weights x corresponding to each score and interpret the result. Pause the video and find these values using the formula here. Okay, number 1 is z equals 1.96. So let's apply the formula. X equals mean plus z times standard deviation. So x equals 9 plus 1.96 times 2 equals 12.92 pounds. All right, let's try number 2. Z equals negative 0.44, so x equals 9 plus negative 0.44 times 2 equals 8.12 pounds. So our answer is 8.12 pounds. All right, number 3, z equals 0. So x equals 9 plus 0 times 2 equals 9 pounds. So our answer is 9 pounds. That's interesting, but what can we interpret from these results? Let's look at a graph of the data. So to demonstrate how the z-score is related to our real-life example, we're going to look at both the z-score data and our x values on 2 lines below the graph. With that in mind, let's look at what we have here. When we graph, remember that our mean is our line of symmetry in the center. So our mean for this data was 9 pounds. So that was the average weight of cat for this vet clinic. So we put 9 in the middle for our second line underneath our z-score line. I know the value of standard deviation was 2, and I can try to figure out where each of these cats are. The first cat weighed 12.96 pounds, almost 2 standard deviations above the mean. So it would be way over here near the positive end. Our second cat weighed 8.12 pounds. That's very close to our mean and definitely within the 1 standard deviation below. And lastly, our third cat was exactly 9 pounds, which would be right on our mean at the center, at 9. Okay, so let's put this all together in the context of a probability problem. Scores for the California Peace Officer Standards and Training Test are normally distributed with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? So if we look at the graph, we can see this is a right-sided question. So we're going to have to do some manipulation. So what do we know? They want to know the top 10%. So first we need to convert that to a decimal format, which would be 0.1. And since the cumulative area under the curve is 1, we could subtract 1 minus 0.1 to get what would be to the left, which would be 0.9. And that's what we'll look at for our table, 0.9, to look for a z-score. We also want to keep handy the other facts from the problem. The mean is 50, and the standard deviation is 10. When we look at the table for 0.9, the closest that we can find is 0.8997. So the z-score that corresponds to that, or the closest one that corresponds to it, is z equals 1.28. So that's the one that we're going to use. So if we use the equation we were given for converting z-scores to find the x values of x equals mean plus z times standard deviation, we sub in our values and get 50 plus 1.28 times 10 and get about 62.8. This means the lowest score you can earn and still be eligible to be hired by the agency is about 63. All right, let's try one more. In a randomly selected sample of U.S. adults ages 20 and over, the mean total cholesterol level is 190 milligrams per deciliter with a standard deviation of 40.9 milligrams per deciliter. Assume the total cholesterol levels are normally distributed. Find the highest total cholesterol level an adult age 20 or over can have and still be in the bottom 1%. So as before, let's remember the numbers they're giving us. Mean is 190 milligrams per deciliter. Standard deviation is 40.9 milligrams per deciliter. And we want the highest and still be in the bottom 1%. So the total cholesterol levels in the lowest 1% correspond to the shaded region shown. This makes sense, right? This would mean the people that have the lowest cholesterol are here at the bottom. And we're trying to figure out the highest cholesterol that would still be in this bottom range. In the table, when we look for 0.01, which is 1%, the closest we can get is 0.0099. The z-score that corresponds to the area is negative 2.33. To find the x value, we use the formula and remember the numbers they gave us earlier. So we find 190 plus negative 2.33 times 40.9, and we get about 94.7. So here's how we interpret that, and I would word this just a little bit differently. The highest total cholesterol level a U.S. adult age 20 or over can have and still be in the bottom 1% of total cholesterol levels in U.S. adults 20 or over is about 95 milligrams per deciliter. That was a mouthful. Very good job in this section. I know there was a lot of detail. Hopefully you followed along and got those shortcuts, and I'll talk to you in the next video.